The particular topic of this talk will be the SEI, the solid electrolyte interface, and I will discuss this on graphite and silicon electrodes. I think you all know this, but to keep us all on the same for the same basis to start with, I have this nice vehicle, and you know that the best vehicles are those that have a battery in the floor, right? The one challenge of these batteries, as you know, is that the state of health decreases in these batteries over time. So it does so doing storage, but also doing cycling. And when we zoom in, of course, you also know that this is not just a metal immersed into a fluid, but it consists of these films. And what I particularly look at is the negative electrode. And to start with, this could be graphite. And when you zoom in further, you see that this is the graphite electrode, and you see the layers of the graphite. And what's important for the aging, or most important for the aging, particularly the calendar aging, is the surface. And on the surface, we form this solid electrolyte interface, and the growth of the solid electrolyte interface is the driver for this calendar aging. But also for cyclic aging, the SEI is a large contributor, and it also interferes with different aging mechanisms like plating. So it's very important to understand how the solid electrolyte interface is growing on the different materials. And this is what I'm going to show you in this talk. So first, I want to give you an understanding of what this solid electrolyte interface is. Actually, it is also so necessary. So for the lithium-ion battery, because our battery electrolytes have a good stability, but particularly on the anode side of the lithium-ion battery, the stability is not perfect. So already at around 1 volt, these batteries tend to disintegrate, so they are reduced by the negative electrode. But we work with graphite electrodes here, or silicon electrodes, or even lithium metal electrodes, and they have voltages very close to 0 volt. So there's a 1 volt of a gap between the stability of the electrolyte towards the electrode that we want to use. And so the luck is that this is stabilized by the SEI. So the SEI is made up of the, I would say, dirt that is there from this electrolyte reduction. So it's a degradation process, but it's surprisingly made up in such a way that it's self-passivating. So this film is slowing down the further degradation of the electrolyte interface. So this is good, right? So it's dirt that we don't want to have, but the luck is that it's self-passivating. And I think that this is one of the most important reasons that we have lithium-ion batteries today. We have the thing in our typical batteries, and we don't know a way around having this really. So we have to deal with it, and that's why we have to understand this. We have. In trying to understand this, me and my collaborators, we try to separate what can happen. And I want to distinguish the initial SEI formation. And for the initial SEI formation, we talk about something like 2 nanometers up to long-term SEI formation from 10 nanometers beyond. Yeah, so initial SEI and long-term SEI. And the initial SEI, that is governed a lot by quantum chemistry and electron tunneling and how the reactions proceed on the atomistic level. So that's not what I'm going to talk about. I will focus on the long-term growth of the SEI. And so that's set in after the first cycle, maybe in the second cycle, but clearly beyond the second cycle in the operation of your battery. And I have now picked up, taking out two particularly relevant degradation mechanisms. So here we have the graphite electrode. Here on top, we have the electrolyte in both pictures. And in the middle, you have the SEI, the solid electrolyte interface. And now the question is, how can the SEI grow? And particularly, there are two ways this can happen. Either electrons from the graphite can traverse the SEI, reach the surface of the SEI, and then reduce electrolyte on the top, and you would have some top growth of the SEI. The alternative explanation is shown here, where solvent molecules, particularly EC and its co-solvent, they can come from the electrolyte, in some way traverse the SEI, then reach the electrode, be close enough to the electrode that they can be reduced at the electrode surface. And then we would have new SEI below, formed below the SEI at the electrode SEI interface. And so this would be some root growth, some bottom growth of the SEI. So I would distinguish between these two mechanisms. Either electrons go through the SEI, then SEI goes on top, or solvent goes through the SEI, and then the SEI would go from the bottom. Okay, and now in recent years, people have made nice nanoscale images of the SEI. So these are some cryotherm images, and people have found that the SEI structure is complicated. We have organic and inorganic components, and it has some substructure where the inorganic components are not just randomly ordered, but for example, inorganic components tend to be close to the graphite electrode, but there can also be islands. The real structure of the SEI is really unclear. Even so this points towards a very important fact. So the SEI is really, really important for the degradation. It's a negative electrode in our lithium-ion battery, but after 30 years, it's 40 years, it's still not really completely understood. So it's really difficult, but there are a lot of universal properties, at least in running systems. And we often see a long-term growth law that is goes with the square root of the time. So the square root of the time is depicted here together with experimental data, and you see this the SEI thickness growing or the capacity fade growing, and this shows you that the capacity fade is the rate of capacity fade is slowing down in time. So this is a square root in time law here, and our the goal of my work and of this talk is now to develop a reductionist model of this solid electrolyte interface, and by this predict new observables that connect model predictions clearly to fundamental assumptions, and in this way we can discern between different model assumptions, and then set up improved models for the growth of the SEI. So first part of the talk will now be about the SEI growth mechanism on graphite. So this is work I started more than 5 years ago together with a PhD student, Fabian Single. And at that time, there was a discussion of 4 different mechanisms in the literature. There's this solvent diffusion mechanism I've explained before. Then people also discussed electron tunneling mechanism, where the electron tunneling to these 1 or 2 nanometer initial layers governs the whole SEI growth. some people did and still do talk about electron conduction as a main mechanism. And then electron diffusion mechanism is also prominent, which I've described before. But so let me particularly explain what this means. So one important way how electrons could diffuse through the SEI would be that we have a neutral lithium interstitials in our SEI, and such neutral lithium interstitials would come about by, so if we have lithium ions here at the graphite surface, and then electrons could jump from the graphite onto our lithium ions, and then they form neutral lithium, and neutral lithium then can diffuse through the SEI and release its electron at the electrolyte. So that's like a lithium ion that you have in your SEI. You give it a backpack, and in the backpack it has its electron, and with the backpack it moves towards the front of the SEI and releases its electron there. So these are the four mechanisms I'm going to discuss. And what the experiment I discuss is an experiment done in Munich in the Jossen group, where the causes here are the experiment. And what they've done is they've done calendar aging at elevated temperatures for 9.5 months. And they did so at different states of charges. And particularly in this experiment, the state of charge was controlled in update cycles. So that the state of charge is really the correct bottom axis in this plot. And now we derived models, simplified models actually, to show how the state of charge dependent of the different mechanisms, the different growth mechanisms, how this would what this would do to the SOC dependence of this calendar aging. And what you can see is that solvent diffusion does not have any SOC dependence. You see that this electron tunneling has some SOC dependence that doesn't fit, and also this electron conduction has an SOC dependence that doesn't really fit. But this lithium interstitial diffusion, because the electron concentration in the SEI is exponentially activated by the electrode potential, this has an exponential dependence on the open circuit voltage, and this then nicely fits to the staging of the calendar aging. Okay, so we deduce from this that some form of electron diffusion is probably very important for the growth of the SEI. Electron diffusion makes it. Okay, and now recently, so we developed some models, some machine learning models to do inverse modeling. So we particularly use these models for parameter estimations, but we can also use them for model determination. So our feature is based on BALFI, which is a standard tool Bayesian optimization for likelihood-free inference. So it is a Bayesian inference mechanism which internally builds up the surrogate of your models, so it can work with, it can run with with slow models like electrochemical models. So that's BALFI. And then we use expectation propagation to discern our data into future features, and then we can do Bayesian inference feature-wise on our data. Second algorithm we use for model determination is BASC, which has been proposed by David Howie and collaborators. And they propose to use the model evidence, so the integration of the model likelihood with respect to all possible parameters to get this this characteristics. And then the highest mean model evidence gives us the model that's most likely. So here I show you how this works. So I show you here data very similar to before, calendar aging, and then the capacity loss as a function of state of charge. And you can see here in blue our prior knowledge, and you see that by increasing the number of samples, our uncertainty interval decreases, and then finally it converges to this orange line, which very nicely fits the data. Okay. You can see it also down in these plots, how the uncertainty of our model decreases. And from this, we can not only get an understanding of the right model parameters, but also about the distribution. It's about their correlations. And so here there's an anti-correlation here between the lithium, between the electron diffusion coefficient and the solvent diffusion coefficient. And so this is not only then fitting the SOC dependence, but also the time dependence at all SOCs. So it's not just a one-dimensional parameter landscape, but a two-dimensional parameter landscape that we can fit at once. And even more so now we can use this techniques of BUSC to do model determination. And so we run it here on the real storage data, and we compare two combinations: solvent diffusion together with electron diffusion, and solvent diffusion together with electron conduction. And what I show here is a logarithm of the model evidence, and you can clearly see that this one is higher. So solvent diffusion plus interstitial diffusion. So most importantly, the electron diffusion for the SOC dependent. That is probably the most relevant mechanism here. And electron conduction, not in no parameter combination, is really an important contribution. So to summarize these findings on graphite electrodes, I show you this slide. So our model in the end predicts capacity fade with this formula. So you and it has two important contributions. First, the concentration of electrons in the SEI is electrochemically activated. This gives you this exponential of the electrode potential, and this leads to the to this state of charge dependent of your capacity. Then also what appears here is the capacity fades that we already have, the SEI thickness. And when you integrate this equation with the with 1 divided by the SEI thickness, you get a square root of time growth shown by this. And now this together, this state of charge dependence and the square root of time dependence can give you that seemingly paradox results, which is shown here. So when some people do storage experiments and they don't control the state of charge, then the state of charge starts to drift. And it appears that it's not a square root of time growth. So for this data here, one would deduce that it's not a t to the 0.5 as for square root of t, but a t to the 0.31 that would fit the data. But if you take the full model, including the SOC dependence and the time dependence, and take into account the SOC drift, then even with the square root of t growth, you nicely can fit this curve with our simulations. So one has to be careful when analyzing such experiments and claiming that it's not underlying square root of t growth. And then we can take our model and bring it from just storage to also cycling. And we analyze what's going on then. And we said that the inner layer is probably about tunneling. Then we have a electron diffusion control regime. And when the SEI is very thick, you will also get into a migration control regime. And then the Gauss law might change from a square root of t to a linear dependence on time. And we, with such a model, we can understand the capacity fade. We can understand that the SEI goes much more severe during charging than during discharging. But particularly at low voltages, we would see this linear regime. And then we validated this model with a lot of data from in a collaboration with Mercedes. So I don't have too much time to talk about this. So if you want much more, you can ask my PhD student Lars von Kolzenberg, who is now working for Porsche about all the details of this. Then we took this model and brought it into our 3D simulation tool that can model the microstructure of batteries and how the electrolyte flows in this microstructure and what is happening in the electrodes, the diffusion of lithium in the electrodes, the conduction of electrons in the electrodes. And we put the our SEI growth model on top. And before this this work, it was really unclear, I would say, why there is heterogeneous SEI growth, because most models looked at this square root of time, and this leads more or less to a homogenization. So every difference in SEI length throughout the electrode gets homogenized by a square root of t. And only with this model that also incorporates this exponential dependence on electrode voltage, we could show that variations in the SEI growth among the electrode can come up. And this is important, not so much for the SEI growth itself, but for its coupling to other mechanisms. When the SEI is has a variation throughout the electrode, when the SEI thickness has a strong variations of 10–20% throughout the electrode, then this is important for effects like plating, for example. And so this, to summarize, so this heterogeneity of SEI growth throughout the electrode depends on this electron diffusion mechanisms and this exponential dependence on the electrode voltage. Okay, so now I move from the rather simple graphite electrode towards the silicon electrode, because we want to develop, of course, new electric vehicles, new batteries with higher, with longer range. So batteries with higher energy densities, and particularly the graphite electrode has a rather low capacity. So to improve the capacity, the silicon material is the first you think of, and then maybe the lithium metal. The challenge with the silicon electrodes is shown here in this cover image of our work. So the silicon has a very large volume expansion that you can see here. And you can also see in this three-dimensional image that when you have a small particle and a big, thick SEI on top, if you put lithium inside this silicon particle, the silicon particle will expand a lot. And in this way, also the SEI on top is stretched. And when the SEI on top is stretched, it's thinning. Okay, so the SEI has a larger circumference, but a smaller thickness. And this is, of course, coming with a lot of stresses in the SEI that are relevant to understand, because ultimately this leads to SEI cracks. And this is not good for the self-preservating behavior of the SEI that I praised at the beginning. So on silicon electrodes, there are real, we have to really struggle with the SEI and think about it. So we build up physics-informed models of the SEI. So we have these transformation tensor. We take into account plastic deformation, elastic deformation, and chemical deformation due to the intercalation of lithium. Mathematically, we put all of this in a free energy, and we do thermodynamics-based models that includes all the coupling, and then we can understand this lithiation, delithiation cycles. And finally, we derive partial differential equations for the silicon and for the SEI, and they show us how the lithium moves in the particle, how the elastic forces behave, and then how the plastic flow of the SEI is looking. And the results look like this. So you see here the SEI volume fraction is a function of SEI thickness. So you have to imagine this is the electrode surface here at the left, and at the right, you have the electrolyte. There's an inner SEI that is very dense, and there's a porous outer SEI. And now doing one lithiation-delithiation cycle, the thickness of the SEI changes, and the thickness of the SEI changes, and at the same time, the porosity of the SEI changes up here. And we can model a long-term cycling with this, and you see how the SEI goes up and down during 12 months of cycling, how the SEI volume changes. If you look, and now with our model, we can do more than just looking at it. We can look inside and try to analyze what the stresses are doing and what's going on. And you see that during lithiation, the stress is suddenly increasing here. So that's the elastic regime. And then there's almost a plateau. That's the plastic regime. So it tells us that very quickly, when you go into lithiation mode, you run into plastic flow of your SEI. So then most of the time, most of your lithiation, you have plastic flow of your SEI. Then you switch here to delithiation, and you have this very strong decrease in stress, and it's changing its sign. So that's again elastic deformation, and then doing delithiation, we are again in a plastic flow regime with almost constant stress. Okay, so if you studied mechanics, you understand this, but the main message of this is most of the time the SEI is in plastic flow. So there's the elastic regime is rather short during cycling of the battery. On the silicon electrode, it's a lot of plastic flow. And then we can understand what this means on average during cycling. We see here during charge, the SEI growing. So then during discharge, SEI being constant. And we see how the SEI thickness goes down during charge and then goes up again during discharge. We can look at long-term behavior of this, and we see that at very low currents, we have still something like that square root of T growth, but at very, but these are not very high rates, right? But at higher rates of C to the 10, in our model, we leave this regime of square root of time clearly, and this goes into a linear regime. And why is that? This we can see here in our model. We see at these very low rates, the SEI stays intact, but at C over 10, which is a high rate in this case, the SEI flow, the SEI deformation is so strong that it cracks through up to the electrode, and within one cycle, it can't heal. Okay, so then there's always a pathway for the electrolyte to come to the electrode. And this means that there's actually not a significant, not a real passivating behavior of the SEI, and then we just have linear growth continuing. And this is certainly something we don't want to have in real batteries. And now we can go one step further and try to understand additional properties of silicon electrodes. And for silicon electrodes, it's challenging, particularly in the if you run them and you want to charge them fast. You see this hysteresis of the OCV, of the potential of the silicon electrode as a function of SOC here. And this hysteresis is a problem because all the energy here in this area between the charge and discharge voltage is lost into heat. And so just recently we came up with an explanation of how we can understand this, and that's shown in this image. So during lithiation, the silicon particle expands, so you can see here, and at the same time the SEI thinnens, and it has a compressive acts as a compressive stress on the silicon electrode. And during delithiation, the silicon shrinks and the SEI thickens, and then it acts with a tensile stress on the electrode. So it's rather the opposite stress in the two parts of the cycling. And now if we take our mechanical model and compare it, we can make it fit exactly to the hysteresis just because of these stresses of the particles. The idea is that, as I told you before, quickly you run into a plastic flow of the SEI. And when there's a plastic flow of the SEI, it has a constant pressure and it acts with a constant pressure on the silicon particle. And this constant pressure can explain this constant hysteresis. And now that's a famous Platt model in engineering that tells you that you reach these hysteresis curves also when you switch in between, like from 25% to 75%. And this feature that you can switch in between and you reach the same hysteresis curve, we also get it from this physics-informed model. And looking a bit deeper, one can also now look at the timescales of relaxation and what actually the OCV is. So the data I've just shown you on the other slides, that was Git data. So we got the OCV by at every SOC waiting until we reach kind of equilibrium of the voltage, some steady state of the voltage. But you can also look at the hysteresis by looking at slow currents and then understanding and then for 0.1 C and then calling this hysteresis. Or you do a full Git like here, and there you would see the difference between the lower ends of these curves, which would be the Git results, and the upper ends, which would be the charge discharge at slow rates results. And by assuming that the SEI is not just plastic, but viscoplastic, which means that the viscosity depends on pressure, and this is actually a common feature in such materials, we can make our model work for both these Git data, but also for the slow discharge. And we can also capture the time scale of such a Git profile, the model. And now it's important to look at what the parameters are for this model. And we use the SEI modulus of 100 gigapascal, which is the red curve. So that's important. If the SEI modulus is 10 gigapascal, then this model doesn't work. And the 100 gigapascal are sometimes are discussed in the literature. So some measurements of the SEI elastic modulus find values in the range of 1050 gigapascal. But if you look at values for the inorganic SEI, particularly on the nanoscale, you have values around 100 gigapascal. So if we say that this is the inner SEI that is important here, then this can work, and it also captures the relevant timescales. And then we also have to look at the Young's modulus of the silicon nanoparticle, and so see here that more or less we get the same results for 100 gigapascal to 200 gigapascal, which is also a valid range for nano-sized silicon. Okay, so with this, I'm at the end of my talk, and I conclude. I've shown you our SEI models on graphite, and I tried to show you our results that indicate that electron diffusion is very relevant here. And this also explains inhomogeneous SEI growth throughout our graphite electrodes. And we have used Bayesian optimization to find parameters and do model identification. On silicon, we built a chemomechanical particle SEI model, and The elastoplastic behavior shows us also the OCV hysteresis of silicon nanoparticles, and the viscoelastoplastic SEI reproduces the full GIT, so also the time scales of relaxations in this hysteresis. So with this, I thank you for your attention.